In this lecture, I want to give an example of how to treat math as data. We treat math as data all the time when we, for example, use sorting algorithms as an example for how to sort. We just put in natural numbers and say, okay, these are the upper and lower bounds. But I want to treat math even more as data by giving you the following example. In fact, the question is the following: why do we have prime numbers? Everybody knows what prime numbers are. These are natural numbers that can only be divided by themselves or 1. Otherwise, you get not a natural number anymore. But why do we have them? They're usually just defined, but there's a real reason why we have them. And in order to understand why we have prime numbers, we need to go back to the Babylonians and Egyptians who invented multiplication. Their number system was a little different. They didn't have the decimal system. They were just working in unary. And in unary, a number like 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is represented like this, with 12 little ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I even have to count them twice to make sure I'm not making a mistake here. Well, as they were representing simple numbers like 4 and 5, everything is fine, and 12 may be fine too, but now think about representing something really large, and you have to think about the fact that the Egyptians even built pyramids, okay? So they needed to come up with some system to shorten this. And of course, you could come up with different number systems, but one thing to shorten this is to think about this. 12 is represented as basically 11 additions to 1, or 12 additions to 0. But basically what we have here is 11 additions to 1. So what could we do to shorten these 11 additions to 1? Well, we could not make additions, we could multiply. For example, 12 would then be represented as 3 times 4. Isn't that neat? So we went from 12 symbols to 8 symbols. Granted, we had to introduce a new symbol, which can create problems, but the point is, right now what we did is nothing else but just basically shortened that description. In another module, we explain that shortening of description lengths is nothing else but compression. And we explain a very, very important property of compression. And that important property is that compression can never be universal and lossless. So let's think about this particular compression. So this particular compression, which we call the multiplication symbol, gives us a new rule on how to represent numbers once I understand the multiplication symbol. But is it lossless? Yes, as a matter of fact, it's lossless, because 12 can be written as 3 times 4, just as above. But then 3 times 4 doesn't lose anything. I can easily convert it back to 12. Okay, so it's absolutely lossless. So the question is, it's lossless, but is it universal? And it turns out it's not. And it cannot be, as we said before, but what does it mean it's not universal? Well, what it means is that there are numbers that multiplication cannot reach. For example, these numbers are 3, right? Yes, we can write 3 as 3 times 1, but that description isn't shorter, right? So we cannot compress all the numbers into a shorter description using multiplication. And in fact, these numbers are exactly the ones that cannot be divided by any other number but 1 or itself. So 2, 3, 5, 7, 11, and so on. So one interesting point here is that compression usually needs something, right? So we need a redundancy, or we need a symmetry, something to exploit. So let's think about the fact, what are we actually exploiting? So for example, we can call a number prime if it cannot be represented by multiplication. Interestingly enough, we are now another number that can be represented by multiplication in a very special way. For example, 9. 9 is 3 times 3. That's interesting. Or the other one that's interesting is 16, which is 4 times 4. These are called square numbers, right? Because if you draw a square of length 3 times 3, or if you do 4 times 4, then the side lengths are the same, so we get squares. So now, the non-prime numbers are the ones that can be shortened in description by multiplication. So that means the symmetry here is they're actually rectangles. So the best way to think about this is to say, okay, so we define a rectangular number as a number that can be presented as some u times v, where u and v are greater equal to, right? And we can find out that this is exactly right. So our 12 would just be a square, a rectangle, obviously, of 3 times 4. Yeah. And this is how we can see data and math as one thing, because ultimately a number is a representation of the description of 12 objects, for example. 12 means 12 objects. It's an encoding for an observation, and in this case the observation is 12 little sticks or 12 little ones in a row.